1, 2, 3, 4.
I know that you're going to fast forward through parts of this. I'm okay with that. Let's see what happens. Alright, so we're looking at buoyancy examples. Just to remind you, the other day we were looking at formulas. Remember, buoyancy is equal to rho g times the volume of fluid displaced. Alright, so One-Eyed Willie, what movie? Oh, Goonies, nice job. One-Eyed Willie, sunken treasure chest, has come to rest on a few small rocks at the bottom of a freshwater cave. The treasure chest is 0.5 meters by 0.5 by 0.3 meters high and contains 100 kilograms of gold. We're going to say that includes the mass of the chest as well. What is the buoyant force exerted on the chest? So, what do? Let's draw a picture. So if I draw my forces, I'm going to have mg acting straight down. Right, so I've got mg down. And then what force is acting up on it? Oh yeah, the buoyant force. I better make that buoyant force lower, or smaller. If I didn't, then it would float. So, what is the buoyant force? I think that's pretty easy. Density of the fluid times gravity times the volume of the fluid displaced. So, since it's fresh water, we've got 1,000 kilograms. Kilograms per meter cubed. Gravity is 9.8. And to find the volume for that, that's pretty easy. 0.5, 0.5 times 0.3. Let me try the pause button. Anyone else get 735 newtons? Good. All right, let's plug that in. And if data created a gizmo to lift the chest, what force would it need to exert to raise the chest at a slow, constant rate? So that's the key right there. Slow, constant rate. Therefore, the sum of the forces is going to be equal to what? That's right, Joel, 0. So if we take a look, we're going to have another force. We'll call that tension acting up on it. So we're going to have plus tension, plus the buoyant force, minus mg equals 0. And then the tension, and this should just kind of make sense, right? It's going to be the buoyant force plus, it's going to be the weight minus whatever force is acting back up on it, the buoyant force. So tension equals 100 times 9.8 minus, we already calculated it, so I'll plug it in, 735, 245 newtons. Sound good? All right, here's the next one. 227 kilogram block of cement of density 2.8 times 10 to the third kilograms per meter cubed rests on a pedestal in front of the Al Capone Memorial Library. How much force was required to lift the block out of the fresh water at a slow, constant rate? Yeah, you guys see a theme here. Good. I'm going to go ahead and draw a picture. So we're going to have the force be down on it, mg. Oh, wait a minute. This is pretty much just like the other problem. Buoyant force and tension. So if I say the sum of the forces causes the mass to accelerate, but this time it's going to be 0 again. Yep. And then I'm going to have plus tension minus the buoyant force sorry, plus tension plus the buoyant force minus mg equals 0. And let's solve it up for t. You know what? I'm going to let you do that. Push pause and do it up. All right, I'm hoping you got to here and then thought, oh, shoot. Wait, what? What do we plug in here? It gives us the density of the object. I see that right there, but it doesn't give you the volume displaced. I think what I would have to do then is to figure out that the volume of the fluid displaced is just going to be, well, let's see, hold on. Density is mass divided by volume. So volume is going to be mass divided by density. All right, that sounds right to me. So I'm going to take that and substitute it in. There we go. So tension equals mg minus density of the fluid times gravity times the mass of the object divided by the density of the object. All right, I'll give it a wipe here. And I think that's everything. Let's plug in some numbers. So I've got, what do we got, 227 times 9.8 minus the density of the fluid. It's going to be 1,000 times 9.8 mass of the object over density of the object. Now, I could have solved for that separately, but this is varsity physics. You guys know that. So, yeah, plug it all in, and this is when I would usually pause and let Amanda get it for us. But, why don't you guys plug it in? All right, Hannah, what's the answer?
So if you did this correctly, you'd get 1,430.1.
And we should probably round that to 1,430 newtons, correct?
Correct.
Thanks. Because too many digits would look stupid, wouldn't it?
Yes.
Yes, it would. There we go. Let's try number 3. Number 3 is kind of a classic, so make sure you're paying attention. It says, imagine a rectangular solid. Imagine a rectangular solid having a height of 1.5 centimeters and a density of 10,500 kilograms per meter cubed, floating in an unknown liquid. Given that the block is submerged to a depth of 1.16 centimeters, what is the density of the liquid? Think ratios. Glad I gave that hint down because I don't remember what to do. I haven't looked at this since last year. But now if I think about it, here's a block. So I'm going to draw a picture and install. Let's see. There it is. Now we're going to have a volume of fluid displaced by the amount that is submerged in the water. And if I draw in my vectors, since it's floating, mg is going to be exactly equal to the buoyant force. So if I say the sum of the forces is equal to 0, I'm going to say plus buoyant minus mg equals 0. I'm still not sure how I'm going to solve this, actually. And I like the fact you think I'm kidding, but I'm not. I don't know. So let's see where it takes us. So if I do buoyant force, density of the fluid, gravity, volume of fluid displaced. That's going to have to do with this h, I'm guessing. Yep. And then mg, the mass of the block. Oh, crap. Did I give you the mass of the block? Nope. That's right, David, I didn't. But what we could do is solve for the mass of that block. What is that formula? What is it? Oh, yeah, density. Density of the object is the mass of the object divided by the volume. So therefore, the mass of the object is just the density times the volume. I know you guys already saw that. It's nice of you to wait for me. Now, if I keep going, then I'm going to have fluid times gravity. There is a chance that I just recorded that whole last number 3, or didn't record it and did all the work. If so, that stinks. There were some really good comments. No, there wasn't, was there? Sorry, Hannah. Hopefully it recorded.
Shouting out people's names.
Yeah, I know, but I don't know if it recorded. Well, let's do number 4. All right, so we're almost 10 minutes into the first video. If this is what we're doing for the next 4 months, we are in trouble. 4 months? No, wait. Whatever it's going to be, if this is it, we're in trouble. But here it is. This is one of my favorite problems, actually. In the 1980s, a man in Los Angeles connected a number of helium balloons to a lawn chair in an attempt to get a better view. This guy is my hero. Now, he sat in the chair with his BB gun and a lunch, and it turns out a 6-pack of beer. But that's not in the problem. And released the tie-down line. The chair, gun, and lunch, and the man have a combined mass of 100 kilograms. The density of helium is given, and the density of dry air is about 1.29 kilograms per meter cubed. We're going to neglect the volume of the chair and the person, but not the balloon. Now, what minimum volume of helium will be needed to lift the system in dry air? And how many 3-meter cube balloons would this be? Now, I knew that you were not going to believe that this was true, so I've got a video. And let's see. Yeah, I'm going to hit play. You ready?
Roger. The country got through its 206th birthday celebration in fairly good shape. The fireworks crowds were down somewhat in Washington and in New York, but St. Louis claimed the nation's biggest gathering, 2 million, along the banks of the Mississippi. There were, of course, foot races and turtle races and balloon races, but there was only one balloon trip like the one Larry Walters of North Hollywood took. Here's David Burrington.
Larry Walters had always dreamed of flying a balloon to a faraway place. So with help from a friend who taped these scenes, he rigged 42 weather balloons to a lawn chair and filled them with helium. Walters hoped to fly across the mountains to the Mojave Desert, staying in touch with a CB radio. Suddenly a cable broke and up he went with one emotion.
Fulfillment. I was on my way.
The first casualty, his glasses. They slipped overboard, leading to this radio transmission with his girlfriend.
Ron, cut him down. You gotta come down if you can't see. Cut him down.
I've got my other glasses. I can see perfectly. Don't worry. You copy, over.
I copy. Are you sure you're okay? There's planes up there. We can hear them. Are you okay?
I'm okay. I'm going through a thin fog layer. Over. My altitude's 1,500 feet. See Marineland right now.
So you can see Marineland. So you're heading toward... Oh, my God. You're going towards the ocean already.
Yeah.
Hey, everybody down here says to cut it and get down now. Cut your balloons and come down now. Everyone wants you down now.
The balloon reached 16,000 feet, spotted by two astonished airline pilots. But the craft wasn't moving, so after nearly 2 hours, Walters shot out some balloons with a BB gun and came down fast over Long Beach, the only time he was frightened.
All I saw were rooftops and power lines. I thought to myself, my God, this is it. You know, please God, you know, don't let me get fried.
Today, Walters said he has no intention of going ballooning again. His first priority now is to sell the rights to his story. David Burrington, NBC News, Los Angeles.
Here.
So first thing you do, shoot, I knew I should have looked this stuff up first, I guess, is to draw a picture. So go ahead and do that. You know what? I think I'm going to use just one balloon to represent all of the balloons. Here we go. And then we'll have Larry and his stuff down here. And then when I think of the forces acting on the system, I'm going to have, obviously, mg down and the buoyant force up. And if the buoyant force is bigger than mg down, then it'll make it. Now, the question's asking, what's the minimum volume needed to lift? So minimum, that kind of tells me that I'm going to look for the sum of the forces to be equal to 0. Like just enough to get it off the ground. So let's see where that takes us. So we got the buoyant force minus mg equals 0. So, okay, we're back to the buoyant force equals the weight. Check. All right. So what's the buoyant force equal to? The buoyant force is going to be the density of the fluid displaced times the gravity times the volume of the fluid displaced equals the mass times the mass of the object times gravity. Now this is what is tricky. The balloon is filled with helium, which is less dense than the surrounding air. But it does have a mass. Yes. So over on this side, the volume of the fluid displaced, let's see if I were to take my pointer like right there. The volume of the fluid displaced would be the volume of the balloon. Density of the fluid, boom, that's the air. But this mass here, that mass has to be for the object and the balloon. Oh my gosh. Physics is tough. I don't know how you guys do it. So if I were to expand this out, I'm going to say density of the fluid, gravity, volume of the fluid equals mass of the object plus, times G, plus mass of the helium times G. So let's take that out. Looks like it gives me the density of helium. So I'm going to do that same substitution I had to do before. Since the density of helium is mass of helium divided by volume. If I go ahead and do this, I'm going to do density of the fluid times gravity. Volume of the fluid equals mass of the object times gravity plus density of the helium times gravity times the volume of helium which we know is going to be the same number. That's one of the keys. I can't believe I can't pause this. I really don't know if I can do this all in one take. We'll find out. Those guys are the same. So how do I solve that up? Ooh, I do see that G's cancel out. And if I were to clean up a little bit, I'm going to have rho F volume equals MO plus rho HE volume, because the volumes are equal to each other. Same balloon. How do I solve that? Oh, yeah, all right. Density of the fluid displaced minus density of the helium. Ooh, I'm factoring out a V in the same step. Varsity physics, baby. Equals the mass of the object. All right, let's see what happens. So the volume equals mass of the object and the difference in density. All right, I'm nervous, actually. What's it say? Oh, he's got 100 kilograms between the BB gun, his lunch, and the beer he brought, apparently. Density of the fluid, 1.29, minus the density of helium, 0.178. Volume of the fluid, you're going to plug that in. Who's plugging that in right now? I'm betting it's Sam. Sam, I think you're in the lead. Oh, no, maybe not. Maybe not. Let's find out. Oh, Adam's already got it. Hopefully he got 89.5. And that number actually sounds familiar. Whew, good thing. So 89.5 meters cubed of helium would be necessary. So how many 3 meter cube balloons would this be? The answer would be 30 balloons. 30 balloons. And a heck of a lot of helium. Helium now is actually getting more and more expensive because it's getting harder and harder to find. So it might not be the most efficient way to do it, but man, it would be so cool. Extra credit if anybody sets this up in their backyard and videotapes it. Actually, no, don't do that. That would be bad. Whew. I can't believe I can't pause this thing. A young woman has a density of 980 kilograms per meter cubed. She's floating in the Great Salt Lake, which has a density of 1,150 kilograms per meter cubed. Approximately what percentage of her body will be above the surface? Well, normally when people are floating on their backs, or when they're floating, they would be floating on their backs. So let's go ahead and draw that. Here's a person floating on her back. Here's the water. She's floating pretty high. Well, it is a salt lake. That makes sense. She would float a little bit higher if that's the case. I'm going to color it in. Right now I'm stalling and giving my brain time to figure out what the heck is going on here. I draw my forces. mg down. Normal force up. Which one's bigger? Oh, normal force. Buoyant force. Which one's bigger? That's right. Neither. Because if the buoyant force was greater, she would float up into the air. That would be awesome. If her weight was bigger, she would sink and drown. That would be bad. So clearly, the sum of the forces is going to be equal to 0. So the sum of the forces equals 0. Buoyant force minus mg equals 0. So I know I just like to write it. Buoyant force equals mg. So the density of fluid times the gravity times the volume of the fluid equals the mass of the person times gravity. All right, easy. So I just solve up for, oh, wait a minute. It's asking for what percentage of her body? Percentage. It looks to me like a certain amount of her body is submerged and a certain amount of her body isn't. So I think I need to find the volumes, difference in volumes. So I'm going back to that same old substitution. Comes up over and over again. Mass of the object. Let's see. Density is mass divided by volume. So the mass of the object is going to be the density times the volume. All right, let's plug that in. And then I think we're going to be rolling. So density of the fluid, gravity, volume of the fluid equals density of the object, gravity, volume of the object. And, oops, I'm going to go thinner. Ready? No, wrong one. There we go. Cross off the G's. And you know what happened was I got distracted because I was trying to think about which one goes over which. How do you do this? Well, obviously the volume of the object, this one, is going to be greater than the volume of the fluid displaced because the volume of the object is like the whole thing, right? Like that's her right there. So that's going to be greater. Oh, my phone's blowing up. You know why? Tom Brady. Oh, this is sad. Very sad. Give me a moment. My phone never blows up about anything. All right, so let's get that in terms of VF over V naught. And I think it's going to be as simple as the densities. All right, so I'm going to call that 85.2%. Now, what does that remind you of? What type of problem? Oh, yeah, we haven't done it yet, but we will. It's the classic, the size of the iceberg beneath the surface of the water. Very similar, setting up a proportion. All right, I got one more problem that I'm going to do for you, and then I'm going to ask you to do the last one on your own. You're getting tired. I know you just fast forwarded that whole thing anyways. So here we go. This is a problem I made up years ago. Back when I was single and living in New York, I made a kayak out of cloth and wood in the basement. Oh, jeez. Oh, I thought those were bags under my eyes. Those are just shadows. Oh, that's bad. Wait a minute. Oh, huh. Oh, the other thing you guys probably didn't notice, but I was trimming my eyebrows the other day, and you know how the running joke has been that I can't see anything. I mistook the 5 for the 2 on the trimmer. It's a wee bit short. All right, last one. An old cloth kayak has a mass of 20 kilograms. Oh, piece of cake. When a young man having a mass of 90 kilograms sits in the kayak in fresh water, it still floats. What is the volume of the water displaced? Oh, all right. Let's just draw a picture. Hope so. Here's a kayak. I'm sure yours will look better. Person sitting in it. Let's draw a paddle. That would look nice. Yeah, there we go. Cool. If I draw my forces, oh, it's floating. I love floating problems. They're so much easier. If it's floating, then the 2 forces acting on it, mg down and the buoyant force up, have got to be equal and opposite. So the sum of the forces equals 0. I can't seem to not move out of the screen. I think it's okay though. The sum of the forces is equal to 0, so we're going to have plus buoyant minus mg equals 0. Buoyant force equals mg. If your parents are watching this for the first time, they're like, why does he always do that? Habit. And what it does is it trains your mind to get to the next step. So density of the fluid, gravity, volume of the fluid displaced equals the mass of the object times gravity. And if I look at this, I've got mass, don't I? Yeah, I got mass. All right. What is the volume of the fluid displaced? Is this really that easy? I think it might be. That goes there, that goes there. Sweet. We haven't had an easy one in a bit. The volume of the fluid is going to be the mass of the object divided by the density of the fluid. So mass of the object is going to be 20 plus 90, so 110. Divided by fresh water is 1,000. So the volume of the fluid displaced is, oh my God, I just got my calculator out to divide by 1,000. Oh man, I'm already slipping. How many days have we been out of school? Not enough. There we go. When place the kayak in the ocean. Oh gosh, don't bother. It's too easy. All right, so here's the deal. Do number 8 if you can on your own. challenge yourself if you get, oh, there's answers. Nice. If you get it, awesome. Looked like the answer to 7A. Hey, we did get it right. Nice job, everybody. I hope you guys are all good. Thank you for going through this. Yeah, I'm going to stop it here.